In this problem, it says find the outward flux of the field F equals xyz, xyz, xyz across the boundaries of the cube. This is the unit cube. X goes from 0 to 1, and the same for y, z. So what's going on is you have this cube like this. You have this unit cube, and what's going on is you have some vector field F. So at each point you have this vector, right? You have all these vectors like this, okay, whatever, just everywhere, all over. This vector field is defined on all of R3. So everywhere inside the cube, outside the cube, on the boundary of the cube, everywhere there's this vector, right? And what the outward flux is what they're talking about is this double integral f dot nds. So it's double integral over the surface S. S is the surface of the cube. It's not D, it's the surface of the cube, f dot n ds. In other words, it's the tangential component of the force, or your vector field. You're taking the tangential component, this f dot dn, this f dot n, f dot n is the tangential component of f on S, on your surface S. So you're taking the tangential component and then integrating the tangential component of f over the surface S. So this is a surface integral. That's called the net outward flux. And to do this integral, if you had to do it out, just using the definition of this integral, S consists of the outside of this cube, so there are actually 6 different surfaces. So you'd have to do 6 different surface integrals and then add up all those 6 surface integrals. But instead, you can do, instead of this surface integral, this vector surface integral, you can apply the divergence theorem. So the divergence theorem says that if your surface encloses a solid, so in this case the solid is D, so it's the solid cube, right? That's D. Your surface, see the squares, these 6 outside squares, they're enclosing the inside cube, D. Okay. The divergence theorem says that this integral, so this is the outward flux. So if your n is pointing outward of the cube, okay, so this would be the outward flux. The divergence theorem says that this is the same as the integral of the divergence of f across D. That's the fact that these two are the same, that's called the divergence theorem. And that's going to simplify the calculation a lot. So let's just recall that the divergence of a vector field is just the sum of the partial derivatives. That's not exactly, no, I don't want to say it's the sum of the partial derivatives. It's, what it is if you have your vector field, which is like F1, F2, F3, then the divergence of F is going to be partial F1 with respect to X plus partial F2 with respect to Y plus partial F3 with respect to Z. Sometimes the notation is this del dot f. And that's something that's like in quote marks, but if you think of the gradient as like this, partial x, partial y, partial z, dot your f1, f2, f3, this is also in quote marks. The thing is that the dot product is like you multiply this by that by that, and that by that, right? Well, this notation, I mean, this doesn't make any sense at all. It's just a mnemonic. It's just a way to help you remember. Instead of multiplying, you do partial x of f1. So it's equal to partial f partial x1, partial f1 partial x, plus partial f2 partial y, plus partial f3 partial z. So it's not the sum of the partial derivatives, it's because you're taking partial derivatives of different functions, right? So this is like a mnemonic to remember. It's not actually like the dot product of this thing with this thing. Okay, it just helps you remember that the divergence is this. So what's the divergence of f in this case? Well, f was xyz, 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 so my f1 is xyz, so is my f2, so is my f3, this example. So when I take, so the divergence of f is partial f1 partial x plus partial f2 partial y plus partial f3 partial z. Partial f1 partial x is going to be yz. Partial f2 partial y is going to be xz. Partial f3 with respect to z is going to be xy. Now, did I say the same thing? I meant yz plus xz plus xy. That's the divergence of f. And so this flux, that's the thing we're trying to calculate, right? This is the thing that the question is asking for. Divergence theorem says that it's the same as this triple integral of the divergence of f. And we know that the divergence of f is what we just found. So the flux, the net outward flux by the divergence theorem is this triple integral of yz plus xz plus xy over the solid D. Now to do the triple integral, you have to pay attention to what your D is. I mean, depending on the problem, you're going to get a different solid D. In this case, the solid is the unit cube, and we know how to set up the integral, right? It's just from 0 to 1, x, y, and z. So we'll do dz, dy, dx. Z goes from 0 to 1, y goes from 0 to 1, x goes from 0 to 1. Of course, you could do dx, dy, dz, or do whatever order you want. It doesn't matter. You're going to get the same thing. So let's do the inner integral. Integral from 0 to 1 of yz plus xz plus xy dz. So the integral with respect to z is going to be y over 2 z squared plus x over 2 z squared plus xyz from 0 to 1, and that's going to be y over 2 plus x over 2 plus xy. Right? Because you plug in z equals 1, you get 1 squared, and then 1 squared, and then 1. And then you subtract 0. Now we do the middle integral. We have to integrate this from 0 to 1 with respect to y. The integral of y over 2 with respect to y is y squared over 4. And then you have xy over 2 and then xy squared over 2 from 0 to 1. And that's going to give you 1/4 plus x over 2 plus x over 2 is going to give you x plus 1 over 4. Now we do the outside integral. We have to integrate from 0 to 1, x plus 1/4 dx, and that's 1/2 x squared plus 1/4 x from 0 to 1. That's 1/2 plus 1/4, that's 3/4. So the answer is 3/4. Let me just check to make sure that this is in fact correct. Yep. Yeah, I'm just looking at something, and then the reference just skips the computation of the integral and just says the answer is 3/4. But this is the computation. Okay, so that's the answer. The flux is 3/4 using the divergence theorem. Of course, let's just make some comments. So we're done with the problem, but if instead of this cube you had a sphere, right, then you have this integral over a sphere, you'd have to use spherical coordinates. If your D ends up being, like the inside of a cylinder, then you use cylindrical coordinates, that sort of thing. So the point is that you get this triple integral, and then you have to pay attention to how to set up the triple integral, and then you do the triple integral, and then that gives you the answer. In this case, it's easy because we just use Cartesian coordinates.